In this lesson, we'll continue our discussion of the chemical level of organization by looking at a molecule that is extremely important to us. This is going to be water. So, water is the most important substance in the human body. It accounts for about 2/3 of our total body weight. Now, I put this picture here on purpose. This is one that we had done in a previous lesson just to kind of review that each one of these here is an actual water molecule. The blue circles represent hydrogens, right? So H2, right? Two hydrogens. And the orange or reddish circle represents an oxygen, H2O. We also saw in previous lessons that this water molecule here is kind of bonded to this water molecule here by a weak electrical interaction, right? An electrical attraction known as a hydrogen bond. Remember we said the negative side of oxygen here is going to be attracted to the positive side of water here. The reason water has a negative and a positive side is the oxygen has a stronger pull of electrons, so the electrons tend to stay over here more than over here. So as a result, water is polar, negative on the oxygen side, more positive on the hydrogen side, right? Water is a polar molecule. Right? So all these dotted lines represent these weak interactions known as a hydrogen bond, and it holds all the water molecules together. Right? So that's just a little bit of a review. So water is so important to, again, our life. We want to understand the specific properties of water. The first one, one of the things about water is a universal solvent. Water has the ability to produce solutions. That's a word you should highlight right here. A solution is a uniform mixture of two or more substances. All right, just as an example, let's say I'm doing this lecture today and I feel like, I've been talking a lot, we're doing these recordings, or I've been teaching in, face-to-face live classes all day. Excuse me, and I feel like my throat is getting a little bit sore just from talking a lot. So you know what? I'm going to go up and I'm going to make a nice, just hot cup of water just to kind of soothe my throat a little bit. So I heat up some nice water and I take a sip of it and I go, wow, this doesn't really taste that good. Let me give it some flavor. So I take a teaspoon of sugar and I put it into this nice hot cup of water and I stir it around. And would everybody agree over the next couple seconds that sugar would dissolve in the hot water? Now I can taste it and it's going to have a nicer taste to it, right? It'll be a little sweeter, that type of thing. Well, what we just produced, believe it or not, was a solution. A solution has two parts. The solvent, that's the liquid part, so that would be the water, and then what we dissolved in it is known as the solute. That would be, in my example, the sugar. Right, so solutes are the dissolved substances. Right, so that's an important word. Right, so a solution, two parts. The solvent, right? In this case, it's going to be water. Water is one of the universal solvents. It can dissolve a lot of different things. And then the solute is what is dissolved in the substance. Right? And we'll see that many molecules are water soluble. I'll go over this again at the end of the lesson. Things that are polar substances. So again, just like water is polar, let me go back, meaning that it has a negative side and a positive side. So any other molecule that's also polar will do really well in water. It will dissolve. Things that are non-polar, things that don't have a charge to it, like oil, does not dissolve in water, right? If you take oil and water, you know they don't mix. Right? And that's because oil is non-polar. It does not have a charge. Any other charged atom, like sodium, chloride, these things are going to dissolve in water. So that's the first property of water that I want you to know, and that's an important one. It is the universal solvent. Again, water can produce solutions. Solutions have two parts. The solvent, which is the water part, and the solute, that's what's dissolved in the water. The second property of water is reactivity. So if you think about it, since our body is two-thirds water, our chemical reactions are actually taking place in water. So water is an awesome medium that allows chemical reactions to take place in them. But water itself can also serve as a reactant in some reactions. If you remember from a previous lesson, we had done hydrolysis, where we added water to do decomposition. Right? So that's where water actually became part of the chemical reaction. That was in a previous lesson. Okay, so universal solvent, reactivity. A third property of water is that water has a high heat capacity, and very simply that means water has the ability to absorb heat and then retain it, right? We don't if you went out into like the cold weather, didn't have a coat on, let's say it was 10 degrees outside and you ran outside for a little bit without a coat, right, all the heat wouldn't come out of your body. That's because water has the ability to retain heat. And we said before, right, we're two-thirds water. Right, so the definition of heat capacity, this is the heat required to raise temperature, a unit mass of a substance 1 degree centigrade. I'm not too concerned about that definition here. That's more of a chemistry definition. My concern is that you understand that water has the ability to absorb heat and it can retain it for a long period of time. The last property of water that I want to go over is just lubrication. We'll see that water is a lubricant in many physiological processes. So this is going to help to moisten and reduce friction. A classic example that we cover usually in lab is when we talk about body cavities. Body cavities have this lining called a serous membrane that produces a thin, watery, slippery fluid that reduces friction around the organs. So as our organs are moving in the body cavities, these serous membranes produce this serous fluid that's going to act as a lubricant. So that would be a good example. Okay, so those are all again important properties of water. Let's take a look at properties of aqueous solutions. Again, an aqueous solution is a watery solution. We said earlier that water is a polar molecule. And again, I can't stress how important that is for you to understand. If I go back to this picture again, oxygen, hydrogen, hydrogen. There's a sharing of electrons here, again, from when we did the bonding lecture, right? There's a sharing of electrons here, one pair of electrons here. Right? So we do have sharing. That's good. That's a covalent bond. But the sharing is not equal. Even though the electrons are all being shared, oxygen has a stronger pull, and they pull the electrons closer to oxygen. They're still being shared. They're just spending more time over here, let's say. As a result, this side of the water molecule is negative. Again, don't worry about that delta sign. I'm not too concerned about that. Just know this side of water is negative. And then in comparison, this side of water here, notice positive, positive. Again, the reason is the electrons aren't spending as much time over here. And what is the charge of an electron? It is negative, right? So if there's less electrons here, this side of the water is positive. Again, don't worry about the delta sign. All right, so this is a molecule that is polar. It has a negative charge on one side, positive charge on the other side. Okay, so water is a polar molecule. Now, that's good. Because water is polar, many inorganic compounds, let's just use as an example salt, NaCl, they can split into smaller molecules when they go into water. That process is known as dissociation. If we take a look here, we had sodium chloride. Right? When we took a crystal of salt, let's say it was out over here, and we dropped it into water, what happens is the polar nature of water causes the sodium and the chloride to split. If you remember from our previous lesson on bonding, that was an ionic bond. water can break these ionic bonds. So now sodium will stay separate from chloride. What keeps them separate is this. Watch this. Sodium is a positively charged ion, right? It's a cation. So notice, guys, water molecules will form a sphere around the sodium, but notice what side of the water molecule is attracted to the positive sodium. Notice it's the oxygens that are facing the sodium. Why is that? The reason is oxygen is negative, right? So there's, again, always remember opposites attract. So the negative side of water, the oxygen side, notice is all facing the sodium because sodium is positive, and that attraction forms this sphere, and that keeps the sodium ion separate from the chloride ion. Let's look at the chloride ion. Watch this. Chloride ion, we said earlier, is negative. So watch this. The water also forms a sphere, but this time, what side of the water molecule is attracted to the negative chloride is the positive side. See, the hydrogens this time are closer to the chloride. Again, also forming a sphere. So we call these spheres a hydration sphere. Let's see if we have that in the notes right here. Polar water molecules form, highlight right here, a hydration sphere around the ions, and that's what keeps these polar molecules in solution, right? This is how sodium and chloride, or sodium chloride I should say, salt, dissolves in water. Right, so a lot of different chemicals will do this. This process of splitting something is known as dissociation. Now, a type of dissociation where we actually form ions is actually known as ionization. It's kind of the same thing as dissociation, but it's telling us that we're forming ions. Okay, so these are known as hydration spheres. And again, if you notice, the way water faces against the ion depends on the charge of the ion. Right? But in either case, whether it's a positive ion or a negative ion, we still get these hydration spheres. Now, glucose also, again, glucose is not something that would form an ion, but it does have somewhat of a charge to it. So when you drop sugar into water, right, you'll have a glucose molecule. Same thing, hydration spheres, excuse me, will form around the glucose, but this doesn't form an ion, so this would not cause ionization because we're not forming an ion. Okay, so let's take a look at electrolytes and body fluids. So a number of ions can form in the body. A lot of times we refer to them as electrolytes because these are inorganic ions, right, charged particles that have the ability to conduct electricity. Now, why is that important for this semester? When we look at muscle tissue and nervous tissue, those are tissues that conduct electricity. You'll see as you come into contact with different patients and different pathologies, when people do have electrolyte imbalances, things like sodium, potassium is a big one that has a big effect on the heart. These can actually be fatal, so making sure that our electrolytes are in normal balance is extremely important. So this chart is more of an FYI. You don't have to study this or memorize it, but this is just showing some common electrolytes in the body. One important one we're going to be doing all semester is sodium chloride. So when this dissociates, we're going to get sodium and chloride. We see that in a lot of chemical reactions. These other ones are a little bit advanced. Next semester in A&P2, if you study buffers, you'll talk about sodium bicarbonate. That's an important one, but these are just some other ones I just think are interesting. You do not have to know these. You do not have to study these. Okay. The next thing we want to take a look at is we want to finish up with a couple other properties that are important to the anatomy and physiology of the cell, especially the cell membrane, which we're going to do in some future lessons. So sometimes things are attracted to water. They are called, or they are referred to as being hydrophilic. Hydro we know means water. Philic or philos, Greek, means to love, right? So there's a water attraction. So things, guys, that are polar, I kind of went over this before already. Things that are polar, meaning that these are molecules that have a positive side and a negative side, and ions, which are charged, they like water. They're going to interact with water. Other substances do not interact with water. And again, my example I always like to give is oil and water. Right? If you took a drop of oil and you put it in water, you know that oil is going to stay as a droplet. That's because oil is hydrophobic. Phobia, we know, is a fear, right? So anything that is, highlight right here, non-polar, molecules that don't have a charge, that'll include like fats and oils, right? They don't have a charge. So they're considered to be non-polar. They will not interact with water. This property here, these properties of water here, are so important for when we need to understand later in the semester how cell membranes are formed. Okay, so hydrophilic is things that are attracted to water. These would be polar molecules, different ions. Hydrophobic, these are things that are not charged, that do not dissolve in water. Okay, last slide for this lesson. So our body fluids contain large and complex organic molecules, things like proteins, and they need to be held into solution, right? They need to be kept into solution. So we're going to see an example of this is known as a colloid. This is a solution, right? So we know a solution has a solvent and then something dissolved in it containing dispersed proteins or other large molecules. So when you study blood in AMP2, the watery part of blood is known as plasma. I'm sure it's something you've heard of. And in plasma, we have a number of different types of proteins, nutrients, hormones, waste products. They're all dissolved in water. We refer to this solution as a colloid. All right, so this is a solution containing dispersed proteins or other large molecules, right, dissolved in the water, and we refer to that as a colloid, right? So a great example of this is plasma. The last definition that I want you to know is that sometimes in water, things aren't dissolved, but they float in water. So a suspension contains large particles that can settle out of solution, meaning that these particles, guys, they float in water. As long as we're moving, these particles will float in water. But if we were to stop moving, right, all movement stop, they would actually settle out of solution. And the example I always like to give is this. If you went to the beach and you grab like a pail, like a small pail, you're playing with some kids or whatever, right, your children, and you go down and you grab some seawater from the ocean and you pick up some sand. As long as you're swirling that water around in the pail, the sand will float in the water. But then when you put the pail down, right, say you're going to have lunch and something to drink, would everybody agree that sand would start to form a sediment at the bottom of the pail? That's an example of a suspension. In the human body, our blood cells, red blood cells, white blood cells, platelets, those cells, guys, are not dissolved in the plasma. They are floating in the plasma. As long as we're moving around, all of our blood cells stay floating in the water. But if we were to just stop moving, and you see this with death sometimes, right? You'll actually see blood cells, blood will pool where it's the lower part of the body, right? And you can actually see that. So, or how about this? If I took a test tube and I took a vial of blood from my arm at the beginning of class, right? If I just kind of put it on my desk here, over the next couple hours, I would actually see the blood separate. On the top would be the plasma, on the bottom would be all the cells. Okay, so that concludes this lesson on a very important chemical to our life known as water, right? H2O.